All right, so this activity that we're going to watch this particular video, and then at the end or the conclusion of this video, you're going to be doing some review problems from the first semester. I'm going to hit the highlights of the first semester in terms of some of the bigger ideas that we studied, and it's a way to kick off second semester with, again, a quick review of the big ideas from first semester. Starts with our discussion of the three major functions that we study in algebra: linear functions, quadratic functions, and exponential functions. And so if you look here on the screen, we provided three tables of values along with the work to assist in determining what type of function each table represents. And it was noted that when you look at tables, you're looking for patterns. And you can see that table 1, table 2, and table 3 have different patterns. Each of them represents one of the three functions: linear, quadratic, or exponential. So for instance, table number 1. Table number 1, you'll see that the difference from the y coordinates as you go down from -1 to 2 to 5 to 8 to 11, you're adding 3 each time. That was the pattern. And for that particular table, this represents, if you recall, a linear function. Table number 2. Table number 2 didn't appear to have a pattern, and in that what we call the first difference, from 2 to 8, you added 6. From 8 to 18, you added 10. And from 18 to 32, you added 14, etc. You didn't seem to have a pattern. But if you recall, if you look past the first difference and look closer at the second difference, you notice that the second difference produced a pattern of adding 4. And that function, anybody remember what that was called? Yep, if you said quadratic, you would have selected the right function. And so a quadratic function, you're looking for the pattern that's in the second difference. Okay, and then table number 3, similar to table number 1, you saw the pattern from the very beginning, except this pattern, you were multiplying from one y coordinate to another. 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27, and so we call this function an exponential function. And when you're given a table, this is exactly the process you would go through to determine whether you have linear, quadratic, or exponential. The question then becomes, what do their graphs look like? Well, their graphs look like this. Well, number 4, this is the quadratic function. And number 5, this is the picture of an exponential function. And a straight line is the picture of what we know as to be the linear function. So we should be able to recognize this by looking at a graph as well. And so you're going to have to do problems like this. You're going to be given a table, probably in your practice today, and you're going to have to decide, is this a linear, quadratic, or exponential? Well, how do we approach this? Just like you saw in the earlier example. We're looking for what's the pattern, and we start with the first difference. So that's how you would do that problem. Also in that first section, we talked about increasing, decreasing, constant, and just a quick review, just by showing you here on the screen. If a function is increasing, that means this would be increasing. As we move that direction, the numbers are getting higher. And so this is increasing here. It's constant. It is constant when it's flat. And it's decreasing. It's considered decreasing when As you go out on the x-axis, the y's are decreasing. And so that's how we determine in a graph what we mean by increasing, decreasing, and constant. Number properties. So we also talked about number properties in the first semester. And so number properties, there were three main number properties. There were the distributive property, the associative property, and the commutative property. And the first example that I'm going to show you, if you recall, this represents, yep, you got it, the distributive property. We use it all the time. You're actually distributing the 3n here and here, and you're multiplying. You see that multiplication done here and here. And so that's called the distributive property. Quick review. In blue, this example and this example, you can see that in this one you're adding, and over here you're multiplying, but it's the same property. It's the commutative property. And what the commutative property says is the order of those two numbers, whether you're adding or multiplying, doesn't matter. You get the same answer. Commutative is just switching. Addition, multiplication, it doesn't matter. You get the same answer. And then finally, the third number property right here, often confused. However, you'll see that the order of the numbers are the same. The order of the numbers are the same. They're equal because as we know, 9 plus 6 is equal to 4 plus 11. They're both equal to 15. And so the associative property is just moving the set of parentheses. So that's why we call this is known as the associative. So the three properties are distributive, commutative, associative. Pause the video, take these examples down in your notes, be ready to use them in your practice today. Okay, adding, subtracting polynomials. Here are two examples where I show you the original. So here's the original problem, and then here's the answer. This is the final answer. Here's the original problem, and here's the final answer. How did we get those answers? Well, it hinged on your idea of, do you understand like terms? It was a key concept throughout the first semester. The concept of what is a like term. So let's analyze these two examples, and we'll do one on our own. First of all, as you look here, x squared and x squared, those are like terms. So if you add the 4 and the 2, you get the 6. Same thing here. If you look at the x and the x, there's really a 1 there and there's a 3 there. That's where they get the 4. And then, of course, this 7 and that 1, they're considered constant terms. There's no variables to them. So you're just adding 7 and 8 to get, or 7 and 1 to get 8. Same thing can be looked at with subtraction. So for instance, here's an x cubed and there's an x cubed. Well, there's a 1 there. 3 minus 1 is your 2, x cubed. There's an x squared here and here. This is actually a negative 1. This is where you have to be careful. And we talk about distributing the negative in because what we really have here is a negative 1 minus 5. This is really a negative 5 here, if you recall. We like to distribute through. And that's how come they're coming and getting the negative 6. Now, this is all review. This is actually a homework problem you did in first semester. And so we finish it out by saying there's no other x term, so that just gets rewritten. Why is it negative? Because, of course, this gets distributed through. And then finally, you'll notice that the positive 8 and the negative 7, well, again, the negative gets distributed through, and you really have 8 plus 7, which is 15. So let's do an example here below so you can see it in real time. Now, going through this kind of fast, but this is review. Slow the video down. Pause it. Make sure you take some notes and move on to the multiplication of polynomials. And if you recall, we multiplied by simply using the distributive property. There was also a couple other methods that we used, the stack method, and there was also the box method. I'm going to just distribute. I'm going to distribute here, here, and here. Again, slow the video down, pause it. It's a review of how we multiply polynomials. And then finally, to wrap up this, we also talked about solution sets and solving equations and inequalities. When we talk about solution sets, we want to be able to describe them in words, describe them in set notation, and write an equation. In some cases, if you have the equation, graph it. In words, the solution's 5. So all real numbers. Where, in this case, x is equal, the solution, in other words, is equal to five. Now let's describe the solution in set notation. Do that in red. In set notation, a little squiggly mark right here. And as I recall, you're going to say all real numbers such that x is equal to 5. And you close out the set notation with that mark again. And then green, well, it's usually when we're going to write it as an equation, write it as an equation or an inequality. In this case, it's just going to be x is equal to 5. So that's what we did in the first semester, being able to write our solution sets in 3 different ways. Our last thing I want to look at today is just basic operations in solving for equations. So we're solving for x. So the first step is to add 3 to both sides, and we show this like that. That goes to 0, and we're left with 4x is equal to 28. Then we divide by 4. That reduces to just x is equal to 7, and there's our answer.